Hello everyone. One way of designing digital circuits is knowing some common building blocks. So these building blocks could be utilized in different scenarios. They could be modified and sometimes they can be used in their standard form also. So if we understand some of these blocks which are very commonly used, they would help us in designing new kind of scenarios, as well as we can use them as such in some scenarios, so it would save some of our design effort. So today we are going to understand how to design two very common combinational circuits. One is called decoder, another is encoder. So we have very small glimpse of what decoder is in our previous lecture. Decoder is like a demultiplexer where you are giving some n inputs and the output is 2 to the power n lines, and the condition is that only one of that line would be true or would be high at one of the time, all other would be low. So this is because decoder is quite a common term, so to make things more narrow, so we are calling it n is to 2 to the power n line decoder. That means there would be 2 to the power n lines and the input is n. So there would be n signals at the input and 2 to the power n signals at the output, each of width 1. So let's take an example of this 3 to 8 decoder, in which there are 3 inputs and there are 8 outputs, and one of the output has to be true. So for example, if input is 0 0 0, then y0 would be true and all other would be false. So this we have anyway covered in our previous lecture also. So yeah, so this is a standard decoder circuit. Now there could be some variations in this decoder circuit. One of the variation is that instead of one being high, one could be low and all other would be high. So for example, if A, B, C all three are 0, then y0 would be 0 and all others would be 1. So it is essentially an inverted output, and we know how to write function for inverted output. So one method we know that if, for example, this was my non-inverted output, if I want to make it as an inverted output, what should I do? I can use De Morgan's law. So in De Morgan's law, what would happen is that A dash, B dash, C dash, and then Y0 dash will become A plus B plus C. So this is one method. The other, we also understand that all of these represent mean terms. If I want to make an invert of that, the corresponding max term would be can be used as an inverted function. So either way, the inverted functions, if the output are inverted, then this the output would be represented by y0 would be represented by A plus B plus C. We know that A plus B plus C would be 0 if A, B, C, all of them are 0, otherwise it is always going to remain 1. And this is the condition with this decoder with the inverted output, that all other outputs would be 1, but only one would be 0 at one point of time, given like whatever is the input. So why do people use inverted output? So mostly it is there are two reasons. One is that in some of the scenarios we understand that if the output is 1, or if the level is 1, then it will consume less power or less energy, or it can also consume less delay. So here we see that in this particular decoder, most of the output would remain 1 most of the time. So for example, if A, B, C is 0 0 0, then only this will remain 0, all others will remain 1. So if the circuit scenario is such that if the input level or output level is 1, it is going to consume less power or less delay, then it is good to have this inverted output. Okay, so this is one. The other is in some of the technologies, like we finally all these gate would be implemented like a transistor. So these transistors could be CMOS, it could be BJT, it could be, and then there are logic families also, ECL, TTL, etc. So in some of the families, it is preferred that if default output is 1 rather than 0. So some of the chips are fabricated with this inverted output. And this concept of inverted output or inverted input is quite generic. So if any of the block like decoder, encoder, or your multiplexer, demultiplexer, if there is a 0, if there is this circle before the output, that means output is inverted. If the circle is before input, then we can say that input is inverted. Okay, sometimes there are some special pins like enable, reset. If this 0 is there, this circle is there, that means that enable is active at 0, not at 1. Okay, so this is a very generic principle which would be applicable everywhere. Now this is about the decoder with inverted output. Similarly, there is another variation where we can have decoder with the enable input. So if decoder is there with the enable input, the functionality would be something like this, that if enable is 1, then only decoder will perform its operation. Otherwise, if enable is 0, then all the output would be 0. Okay, now if I want to perform such an action where if enable is 0, then all the output has to be 0, and if enable is 1, then all the output has to be dependent, then the decoder operation will work. So that means I have to, whatever is the final output of my standard decoder, then I can AND them with E or enable. So or if I want to directly use my enable, so I can have this 4 input AND gate where the input to these AND gates are corresponding to the mean term. So one of the input is E or enable, and other is, for example, for Y0 it is A dash, B dash and C dash, for Y1 it is A dash, B dash and C, so on and so forth for all others. So essentially E is being ANDed with each output, or it can be given as a input of this, like we can have a 4 input AND gate instead of a 3 input AND gate. Now so when we look at this circuit, when we look at the output functionality or this Boolean expressions, we recall something. Oh yeah, this actually looks like a demultiplexer. The only difference is there, instead of enable, we were calling this as an input, and this ABC were called as control. Now in other words, if I have a decoder with the enable input, I can call it a demultiplexer also, or wherever I require to use demultiplexer, I can use this decoder with the enable input. So essentially this way, if I make this as a standard circuit, and if I keep enable all the time as a 1, so then this whole circuit can work like a standard decoder, which is 3 to 8 decoder without enable. And if enable is 1, enable is a different input which is connected to enable, then this would be a decoder with enable. Similarly, if this enable input is connected to some other input which I want to demultiplex, then this whole circuit can also work like a demultiplexer. See how different utilities can be formed with the same standard circuit, or same standard combination. Now there is another application of this decoder with enable. So this decoder with enable gives us a nice way to create a hierarchical decoders. So let's say I want to create a decoder which is very large, then I can use this decoder hierarchically. It is in the same way we have used multiplexer in a hierarchical way, and advantages are also similar. So you see, instead of having n inputs, so for example I want to if I want to have a large fan-in gate, so because of this hierarchy I can break that large gate into smaller gates. So here with an example, what I am showing is that if this 3 to 8 decoder I need to convert into hierarchically. So what I can do is I can create 2 to 4 decoders. So there would be two such decoders required. Then this enable input, for the first decoder I can give A dash as an enable, and for the second one I can call this A as enable. So the first one A dash is a enable input, and for the second one A is an enable input. So that means if A dash is 0, then this particular one would be active. So that means B and C would tell me about y0, y1, y2, y3, because A dash because A is 0, so this particular decoder is enable. Now if A is 1, that means this decoder will always give me 0 output, and my output would be determined by the second decoder. That means either of these y4, y5, y6, y7 would be active based on B and C values. So essentially what we are doing, we are keeping this among this A, B, C, A was the most significant bit, so we are keeping that at the we are keeping that as an enable. We are using that to generate my enable signal. Most significant one I am using as to generate my enable signal, and the least significant one, because I am using 2 to 4 line decoder, so that means I require 2 inputs, so the lower significant 2 bits I am using as the main input. Okay, and I am keeping all of this in such a way that so that I can arrange my y0 to y7 in such a way that when A dash, or basically when A is 0, then y0, y1, y2, y3, the output is y0, y1, y2, y3, and when A is 1, then the rest of the 4 are marked as y4, y5, y6, y7. Yeah, so the same thing, to make it generic, I can also put it like this. So this is 1 to 2 line decoder when A is the input, so that means there would be 2 outputs, 0 and 1. 0 means A was 0 and 1 means A was 1. And 0 I can give this to enable of first decoder, and 1 I am giving to enable of the second decoder. So that means this A dash and A which I am giving as an input was also essentially like a decoder. Only 1 to 2 line decoders. Input was 1 bit and there were 2 outputs. Similarly, if I want to create any kind of a hierarchy, I can create it like this. So these are 2 levels. This is first level, this is second level. Now let's take a bigger example. Let's say I want to design 8 to 256 line decoder. This is a more realistic scenario. We won't be using this kind of a circuit where we are trying to use only 3 to 8 decoder and we are using 2 levels. But it would be more concerned, more helpful when we are creating larger decoders. Okay, so you want to design 8 to 256 line decoder. Now, otherwise, what would happen in a monolithic design, in a single level design, or in a monolithic design? There would be 256 AND gates. Each of these AND gate would have 8 inputs. If enable is there, then there would be 9 inputs. Now, if I want to design a 9 input AND gate, eventually that AND gate has to be again designed into multiple logic, multiple AND gates. Okay, so that would increase the cost. Otherwise, if I am using a monolithic design of one 9 input AND gate, then the delay would be much more. So that is why it could be a better idea to go for a hierarchical design from the first place itself. Could be multiple ideas here. So let's say I want to make a hierarchical design, I want to make it a 2-level design. In 2-level design, one thing I can do is at the first level, there could be 4 to 16 decoder. And at the second level also there would be 4 to 16 decoders. Okay, so there are 16 decoders, 4 to 16 at the second level. Total number of AND gates are going to be more. So you see, in the second level itself, there is going to be 16 cross 16 AND gates. But number of input to each AND gate would be 5. So because it is 4 to 16 decoder, 4 inputs plus 1 enable input. So there would be 5 input to all of this 256 AND gate at the second level. Similarly, at the first level also, because it is a 4 to 16 decoder, now in the 4 to 16 decoder there would be again 16 AND gates with 5 inputs each. Okay, so because 5 input may again be large, so instead of 2 levels we can again go for 3 levels. So whenever we are breaking things into multiple level, what would happen that your MSB will go in the first level, and then your next level of bits would go into second level, and the next level of bits will go into third level. So these bits will be divided like this. You can always ask a question that why not to divide bits in the other way. So why can't we have let's say bits in a reverse order? We keep our LSB. So this can be understood from this example. So let's say instead of A, if this has been C, least significant one, and A and B we are keeping it here, A and B we are keeping it here. So what does it mean is, then this would have been because A is the least significant one, so A means 0. So whenever A is 0, then these would be up. So that means this output would have been Y0, Y2, Y4, Y6. And when A is 1, then this particular decoder would be active. So that means these output would be Y1, Y3, Y5 and Y7. So although other combinations are possible, there is no harm in that, but the issue would be that you have to jumble up these lines. Okay, so this is the simplest example. If the example is like this, where you are creating 8 to 256 line decoder, then the jumbling would be so much that we will be crazy in solving them back, or in basically straightening them back. So that's why it is a good idea that we keep our MSB at the first level, and then going for the lower significant bits to the next levels. And then we can arrange them in such a way that we can simply call that as a decimal number 0, 1, 2, 3, 4, 5, 6 up to 255. Sorry. So this way these decoders can be designed hierarchically so that they are efficient, and there is another advantage of designing things hierarchically. So some of these decoders, like 3 to 8 decoders, or 4 to 16 decoders, they are also available as packaged ICs or packaged chips. So because they are available as a packaged chips, means prefabricated chips, so we can use them in breadboard. Because they are prefabricated, they are available as ICs, so we can use them in breadboard and we can use them directly. So if we are able to use them directly, then we can use multiple of them to create even larger pieces. So that's why it is good to have generic component at lower level, so that we can create a higher component or a better component, bigger component using them. Okay, so there is also now I'll see one more advantage, one more application where we can use these decoders. So these decoders can essentially be used like multiplexers. These decoders can also be used to design any generic circuit. So in our previous module we have seen any generic circuit means either it would be sum of product or product of sum, and if it is sum of product, then I can also further generically tell it as sum of mean terms, or classical sum of product, or canonical sum of product form would be sum of mean terms, or similarly canonical product terms could be canonical product of max terms. Okay, so if those sum of mean terms and max terms are there, then also we can create it. So it's a pretty straightforward to understand. You see that ABC was the input, and all of these output were representing only one mean term, because they were only representing each output was representing only one mean term. So if whatever is the function, let's say function was this f a b c, we want to have a sum of mean term 1, 3 and 5, then I can have an OR gate which is doing an OR with line number 1, line number 3 and line number 5. So I can have this function. Similarly, product of max term can also be there. So there the decoder would be with inverted outputs, and if it is with inverted output, then each of this line would be representing one max term. And then in the end we can have a AND gate. This AND gate can represent that function which is sum of product. So if it is in the form of inverted output, my decoder is in the form of inverted output, then I can design it using product of max terms, or if it is as a standard form, then I can use it as a sum of min terms. So this way decoder can be used to design or to design any generic circuit. I require additionally one OR gate or one AND gate. Okay, so this is about decoders.